There we go. Looks like everything's working. All right. So today we are going to finish up chapter 2, which covers the infinite series convergence. Okay. So let's say, for example, move this up away. Here we go. We wanted to evaluate the series. Let's say we have the sum from n equals 1 to infinity of 1 over 2 to the power of n. It's where series and series keep making my phone start talking. Okay, so you want to use that to show its convergence or divergence. And we want to use partial sums. Okay, so the first thing we have to do is find the pattern. Of the partial sums. Okay, so if we look at the sum from n equals 1 to infinity of 1 over 2 to the power of n, then that'll give us 1/2 when n is equal to 1. When n is equal to 2, we get 1 over 2 squared, which is 1/4. When n is equal to 3, we get 1 over 2 to the third power, which is 1/8. When n is equal to 4, we get 1 over 2 to the fourth power, which is 1/16. And we can keep on going. But that should be enough to kind of get a pattern going. Okay. So we know that our first partial sum is just the first term, which is 1/2. And our second partial sum is we add the first two terms. So it's 1/2 plus 1/4. We'll change that 1/2 to 2 over 4. Then we get 3 over 4 as our second partial sum. Then our third partial sum is equal 1/2 plus 1/4 plus 1/8. This is just the sum of the first three terms. Okay, which is equal to 7/8. Once you turn 1/2 into 4 over 8, 1/4 into 2 over 8. And the fourth partial sum is just adding the first four terms. So that's 1/2 plus 1/4 plus 1/8 plus 1/16. Okay. And honestly, if you're doing this by hand, you can just hit these first three, know that's 7/8. Multiply this by 2 over 2. So you have 14 over 16 plus 1 over 16 is 15 over 16. Okay. And again, we just keep on going and going and going. Okay. So if we get all of our partial sums, so we give it kind of a general idea. So let's say S of n is equal to the first partial sum. Well, the whole partial sum is just all of the terms. So you have 1/2 plus 1/4 plus 1/8 plus 1/16, etc., etc., etc. But we know if we add all of those partial sums together, if we look at the pattern, we can see our denominator make that equal to still 2 to the power of n. But if you look at the numerator, it's always that 2 to the power of n minus 1. So when n is equal to 1, 2 to the first power minus 1 gave us 1. 2 squared minus 1 gave us 3. 2 to the third power minus 1 gave us 7. So we know each denominator is that 2 to the power of n minus 1. Or really, you could just look at, even if you didn't want to come up with this formula, you can kind of look and see that this number is just getting closer and closer and closer and closer to 1. So the more values you plug in, your answer of your partial sums will just keep getting closer and closer and closer to 1. So this part here was kind of a little bit of extra. But just to answer it, you just have to look at the pattern of your answers. Okay, just the fact that this is getting closer to 1. So we know that the sum from n equals 1 to infinity of 1 over 2 to the power of n converges to 1. Now, if they didn't specify that they wanted the partial sums used, there's always another method. And that's if you take the limit as n approaches infinity. If you did happen to see those values, and let's say you couldn't figure out where it was converging to. Let's say you have 2 to the power of n minus 1 over 2 to the power of n. You can see as n gets bigger, the numerator and denominator just both get bigger and bigger and bigger and bigger. So you have infinity basically over infinity. Which is an indeterminate form. Which means we can use L'Hopital's rule. So we know that this limit is equal to the limit as n approaches infinity of the derivative of your numerator divided by the derivative of your denominator. Okay, so we know the derivative of 2 to the power of n is 2 to the power of n times the natural log of 2. Minus the derivative of 1 is just 0, so that disappears. Divided by the derivative of 2 to the power of n is 2 to the power of n times the natural log of 2. Okay, where anything divided by itself is just 1. So that leaves us with the limit as n approaches infinity of 1. Well, we know that the limit of a constant is always just that constant, so it's still 1. So it converges to 1. Okay. So again, this is just in case you look at these values and you were able to figure this out. So if you were able to figure this out, you're going to just apply it to the limits. But if you can't figure this out, you can kind of look at your partial sum values and see if you can figure out the pattern that way. But this is just a way to avoid having to try and figure it out. At least as far as like guessing where it's going. Using the limits, you get an actual convergent value. All right, any questions on that one? All right. Looks like everyone's done writing. Okay, so let's say, for example, if using partial sums, find the behavior of the sum from n equals 1 to infinity of 8 divided by 6n squared plus 6n. And by find the behavior, they just mean converge or diverge. Okay, so if we want to use partial sums, with this one, we notice we can factor a 6 out of our denominator. Actually, a 6n. But we're going to leave the n, and we're just going to factor a 6 out of the denominator. So we're going to rewrite it. And that 8 over 6, we're just going to bring it out to the front. Times the sum from n equals 1 to infinity of 1 over n squared plus n. Okay, so again, we're just going to start with our first partial sum. That's just equal to 8 over 6 times, if you plug in n equals 1, that's 1 over 1 squared plus 1, which is just 1/2. Okay, so I'm going to leave it like that, just because it looks like our series is the one that's going to be changing. So you kind of want to see the pattern of it changing. So the 8 over 6, we can leave it that way. But if the numbers are small enough, we might be able to see a pattern. Okay, so let's look at our second partial sum. That gives us 8 over 6 times, so we plug in n equals 2. That's 1 over 2 squared, which is 4, plus 2, which is 6. Nope, hold on. Nope, plus 2, just let me see. Oh, duh, thinking of the wrong thing. I'm plugging it in the values. I forgot the S2 is just the first two sums. Plus 1, 6. Some odd reason I was getting ready to multiply it. Okay, so we get our first partial sum plus plugging in n equals 2 gave us 1 over 6. So that gives us 8 over 6. If we multiply this by 3 over 3, that gives us 4 over 6, which we can simplify to 2/3. And it looks like a little bit of a pattern starting again. But let's do our third partial sum. So we have 8 over 6 times, third partial sum is just the sum of the first, the second, and the third. So you plug in 3, you get 1 over 3 squared, which is 9, plus 3, which is 12. So we have 1 over 12. Okay. Well, we already know this is 2/3 for 1/2 plus 1 over 6. So if we multiply 2/3 by 4 over 4, we get 6 over 12 plus 1 over 12. Yep, let me double check. That is 1/2 plus 1/6. Yep. Yep, 4 over 6, 2 over 3. So multiply this by 4 over 4. That gives us 8 over 6 times 9 over 12. Okay, I don't know why I was drawing a blank there. So we have 9 over 12, which is 3 over 4. I know, it's always the little simple stuff that throws me for a few seconds. And if we do the fourth partial sum, that's just 8 over 6 times 1/2 plus 1/6 plus 1/12 plus that fourth partial sum, we plug in n equals 4. That's 1 over 4 squared, which is 16 plus 4, which is 20. So that gives us 8 over 6. And we know 1/2 plus 1/6 plus 1/12 is 3 over 4. So if we multiply that by 5 over 5, we get 15 over 20 plus 1 over 20, which is 16 over 20, which simplifies to 4/5. Okay. Which is another reason I kept it separated, because now if we add these two together and get 2/3, then all we have to do is just say, okay, I know this is 2/3, then add the next one. Then we can say, okay, I know this is equal to 3/4, then just add the next one. So you're not adding more than just two terms at a time. Just makes it a little easier. Not easy, but a little easier. Okay, so let's do one more partial sum. That's 8 over 6 times 1/2 plus 1/6 plus 1/12 plus 1/20 plus our fifth partial sum. So if we plug in n is equal to 5, we have 5 squared, which is 25, plus 5, which is 30. Okay, so we know that these 4 add up to give us 4/5. So if we multiply this by 6/6, we get 24/30 plus 1/30 is 25/30, which we can simplify to 5/6. And it keeps on going. So now we have to try and see if we can find the pattern for those answers. Okay. And we know they're all multiplied by 8/6. But we also notice that the numerator is always 1 less than the denominator. So that appears to be the pattern. So our pattern is just that we have 8/6 times n divided by n plus 1. Okay, so now we have to see if that converges or diverges. If the limit gives us a real number, then we know it converges to that value. If it gives us positive or negative infinity, or if it's undefined, we know it diverges. Okay, so we take the limit as n approaches infinity of 8/6 times n over n plus 1. Okay, so that 8/6 is just going to factor it out to the front just to get it out of the way. Times the limit as n approaches infinity of n divided by n plus 1. Okay. And we can simplify this by dividing each term by n, or think of it as multiplying the numerator and denominator by 1/n. So that gives us 8/6 times the limit as n approaches infinity. N times 1/n is just 1. And n times 1/n again is 1, plus 1/n times 1 is just 1/n. Make that a little clearer. There we go. Okay, so if we take our 8/6 and bring that over, times, if we apply the limit to the numerator and denominator, the limit of 1 is just 1, over the limit of 1, again, it's just 1, plus the limit of 1/n as n approaches infinity. Again, whenever you have a constant divided by a number that's getting bigger and bigger and bigger, that limit is always going to be 0. So really, this is just 8/6 times 1, which is just 8/6, which simplifies to 4/3. And if we wanted to, we could have simplified the 4/3 a long time ago, but just decided to wait till the end. So since that limit is a real number, we know that the sum from n equals 1 to infinity of 8 divided by 6n squared plus 6n converges to 4/3. All right. Any questions on that one? right, so now we are going to look at what is called a telescoping series. And a telescoping series is easy to spot because it has the form where if you take your partial sums, it's going to be some value b number 1 minus some value b number 2 plus some value b number 2 minus some value b number 3 plus b number 3 minus b number 4, and it's going to keep that pattern up till you take some value b sub n minus some value b sub n plus 1. Oops, make that a little closer than I'd like. Okay. So our b number 2 cancels out. If you add them together, they equal 0. Same with b number 3, they cancel out. And it keeps on going in that pattern until all you're left with is your value b number 1 minus your b sub n plus 1. Okay, so if you take that limit, you'll automatically know that this converges to our partial sum value s, which is equal to the limit of a constant b number 1. That's just going to be b number 1. So that's just b number 1 minus the limit as n approaches infinity of b sub n plus 1. Okay, so whenever you plug in your n's and you see the middle terms all canceling each other out, you know it's a telescoping series. So let's say, for example, we know that the nth partial sum of the series, the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1. We want to find the behavior. And again, find the behavior is just a shortcut way of saying does it converge or diverge. Okay, so we know that the sum, I'm just going to rewrite it. You don't have to, but for me it's kind of habit. 1 over n plus 1, that's equal to, if n is equal to 1, then we have 1 over 1, which is 1, minus 1 over 1 plus 1, which is 1/2. Plus, now we plug in n equals 2. We have 1 over 2, which is 1/2, minus 1 over 2 plus 1, which is 1/3. Plus, if we plug in n equals 3, we have 1/3 minus 1 over 3 plus 1, which is 1/4. And we can kind of see the pattern from there. So we know that's just going to keep on going till you reach some 1 over n, that's eventually going to cancel out when you plug in some nth value, minus 1 over b sub n plus 1, which is 1 over n plus 1. So that will be your b sub n plus 1. Because all of these terms in here are just going to cancel out. At 1/4, it'll be a positive 1/4 over here. Okay, so we can know what it converges to. S is equal to your b sub 1 minus the limit of b sub n plus 1 as n approaches infinity. Well, in this case, your b sub 1 is 1. And this is your b sub n plus 1. So this is just going to equal your b sub 1, which is 1, minus the limit of your b sub n plus 1, which is 1 over n plus 1, as n approaches infinity. Okay, so we know this is going to equal 1 minus, again, the limit of a constant divided by a number that's getting infinitely bigger is just 0. So we know S is equal to 1. So we know that this series converges to 1. All right. Any questions on that one? All right. Anyone still writing? Okay. So let's say, for example, if we wanted to determine if the series the sum from n equals 1 to infinity of 14 to the power of n plus 2 plus 14 to the power of n plus 3 is a telescoping series. And with this, you just want to plug in values and see if there's a pattern, if those middle terms cancel out. So the sum from n equals 1 to infinity of 14 to the n plus 2 power plus 14 to the n plus 3 power. We know that's equal to, plug in n equals 1. We get 14 to the 1 plus 2, so 14 to the third power, plus 1 plus 3 is 4, so it's 14 to the fourth power. Now we plug in n equals 2. 14 to the 2 plus 2 power is 14 to the fourth power, plus 14 to the 2 plus 3 gives us 14 to the fifth power. Plug in n equals 3. We can kind of see here 14 to the 3 plus 2, so we have 14 to the 5th power plus 14 to the 6th power. And it keeps on going until we eventually reach some finite number n. And move that over a little bit. (14 to the n plus 2 plus 14 to the n plus 3). Okay. So we can see that none of these middle terms cancel out. So since none of those middle terms cancel out, we know it's not a telescoping series. So none of the middle terms cancel out. So it is not a telescoping series. Oops, bring that up a little bit. All right, any questions on that one? All right. Okay, so what if we wanted to determine if the series sum from n equals 1 to infinity of 6 times cosine of 1 over n to the 5th power minus 6 times cosine to 1 over n plus 1 to the 5th power is a telescoping series. Now this one looks a little more promising because it's subtraction. You have the same terms, but the only difference is one is n and one is n plus 1. So there are instances where that wouldn't be a telescoping series, even though it looks like it would be. But in this case, it looks like it might be, but we can always verify it. Okay, so let's say, I'll go ahead and rewrite it since I always do it. 6 times cosine of 1 over n to the 5th power, and 6 times cosine of 1 over n plus 1 to the 5th power. So we know that this is equal to, when we make n equal 1, bring that down a little bit so we have some room to write. We know that's going to equal 6 times cosine of 1 over 1 to the 5th power, which is just 1, so we can just leave it as 1 to the 5th power. Because it doesn't really matter if it's simplified or not, especially if it's just going to cancel out. Uh-oh. Add an extra parenthesis for some odd reason. There we go. Minus 6 times cosine of 1 over 1 plus 1 to the 5th power, so we'll just leave it as 2 to the 5th power. Plus, since it all can't fit on one line, when n is equal to 2, that's 6 times cosine of 2 to the 5th power well, 1 over 2 to the 5th power, minus 6 times cosine of 1 over 2 plus 1 to the 5th power. So 1 over 3 to the 5th power. Plus, now we make n equal 3. We have 6 times cosine of 1 over 3 to the 5th power, minus 6 times cosine of 1 over 3 plus 1 to the 5th power, so 1 over 4 to the 5th power. So you can kind of see that pattern there. And that keeps up all the way until you reach some value in where it's plus 6 times cosine of 1 over n to the 5th power minus 6 times cosine of 1 over n plus 1 to the 5th power. Okay, so if you see the pattern, we can see we have negative cosine of 1 over 2 to the 5th power and cosine 1 over 2 to the 5th power, well, times 6. So those two cancel out. We have negative 6 times cosine of 1 over 3 to the 5th and positive 6 times cosine of 1 over 3 to the 5th. So those two cancel out. So we can see it's going to keep going in that pattern where it's just going to keep canceling out. Eventually, this is going to cancel out. We're only left. Well, we'll leave it as that one. Is equal to your b sub 1, which is 6 times cosine of 1 over 1 to the 5th power, which is cosine of 1, minus your b sub n plus 1, which is 6 times cosine of 1 over n plus 1 to the 5th power. Okay. So you can see that this is a telescoping series. It's going to be a very irritating chapter. My phone keeps saying every time I say series. Didn't know it was that sensitive. All right, any questions on that one? All right, so let's say if we wanted to find the sum of telescoping series. So if we want to find the sum of the telescoping series, so the sum from n equals 1 to infinity of e to the power of 9 divided by n minus e to the power of 9 divided by n plus 1. So sometimes they'll tell you it's a telescoping series, so you don't have to figure it out. So since they told us it's a telescoping series, so since we know It's a telescoping series. That means we automatically know that its sum is equal to b sub 1 minus the limit as n approaches infinity of b sub n plus 1. Okay, so we always know which is which because our b sub n is e to the power of 9 divided by n, which means our b sub 1 is just e to the power of 9 divided by 1, which is e to the 9th power. And your b sub n plus 1 is just the second term, e to the power of 9 divided by n plus 1. Okay, so our sum is equal to your b sub 1, which is e to the 9th power, minus the limit as n approaches infinity of your b sub n plus 1, which is e to the power of 9 divided by n plus 1. So we take our e to the 9th power, which is just a constant value, minus the limit as n approaches infinity. Here you have a constant divided by a number getting bigger and bigger and bigger and bigger and bigger. Well, we know that is going to be 0. So this is just e to the power of 0. So we know that our sum is equal to e to the 9th power minus any non-zero number to the power of 0 is just 1. So this converges to e to the 9th power minus 1. Make that a little neater. All right, any questions on that one? Okay. So again, the ones where they tell you it's the telescoping series, those are the easiest ones because you can just go right to the formula. All right. Again, not easy, just a little easier than the others. Okay, so now we're going to take another look, well, more in-depth look at the geometric series. We kind of tiptoed around it before. The geometric series is the sum from n equals 0 to infinity of a constant times r to the power of n, where your ratio is to the power of n. Okay. So that has the form, if you plug in n equals 0, you have r to the power of 0, which is 1. So the first term is just a. Plus, you plug in n is equal to 1, you have a times r. Plug in n is equal to 2, you have a times r squared. And it keeps on going till eventually it reaches some finite value n, but it goes to infinity, so we keep on going even after that. Okay, so we can use a geometric series, which we're going to do a lot going forward, to show convergence or divergence. Convergence of a geometric series. Okay, so a geometric series with a ratio that we will call, of course, R, diverges if the absolute value of R is greater than or equal to 1. Okay. Now, if that ratio happens to be between 0 and 1, then we know it converges. So if that absolute value of R is between 0 and 1, then the series converges, and it converges to a specific sum. So to the sum from n equals 0 to infinity, a times r to the power of n converges to a divided by 1 minus r. But only when that absolute value of r is between 0 and 1. Okay. Now, sometimes you can have a series that look completely different, not completely, but different from this one and still be a geometric series. So just because it doesn't start at 0 doesn't mean it's not a geometric series. So if we have the sum from n equals 0 to infinity of a times r to the power of n, we will get the very same collection of sums, or collection of terms rather. We have the sum from n is equal to 1 to infinity of a times r to the power of n minus 1. So if you plug in n is equal to 1, you'll get r to the power of 0, which leaves just a times 1. And then it keeps going and going and going. Or you could even say the sum from n equals 1 to infinity. Let's say n equals 2 to infinity. A times r to the power of n minus 2. Plug in 2, you get exponent of 0, which is just a. Then 3 minus 2, you get 1, 4 minus 2, and keeps on going. So there are so many different ways you can write it, and it still ends up being a geometric series. So you don't want to get too locked in on this form because it can show up in other ways. I mean, the first form is the most common, but it's not the only one. Oops, straighten that up a little bit. All right. Any questions on that so far? All right. So let's say, for example, we wanted to determine if the geometric sequence, geometric series, I'm a couple days late, still yelling sequence, converges or diverges. And that series is the sum from n equals 1 to infinity of -3 times 8/7 to the power of n minus 1. Okay, so if you notice, you have the sum from n equals 1 to infinity of -3 times 8/7 to the power of n minus 1. If you plug in n equals 1, you have the power of 1 minus 1, which is 0. So 8/7 to the power of 0 is just 1. So that's -3. Plus, plug in n equals 2. You can put -3 times 8/7 to the first power plus -3 times 8/7 to the second power, and it keeps on going. So we can see here that this is a geometric series, since they already told us. So this is just kind of showing you the form, how it would look. So if we want to know if it converges or diverges, all we have to do is remember sum from n equals 1 to infinity of a times r to the power of n minus 1. That means that a is equal to -3, and the absolute value of r is equal to 8/7, which is greater than 1. So when that absolute value is greater than 1, we know it diverges. Okay, so really this is all you needed. This part up here was just extra. So you don't have to do that when they tell you it's a geometric series. So with this one up here, I don't want you to think you have to do that every single time. So I'll make this as just a note. So when they tell you it's a geometric series, all you have to do is line it up, find your A and your R, and just look for the absolute value of your R. And if it's bigger than 1, it diverges. If it's less than 1, it converges. Okay. So what if we had the same question, but it was for the sum from n equals 1 to infinity of -5 times 2 to the power of n minus 1. So again, if we have the sum from n equals 1 to infinity of a times r to the power of n minus 1, we match those up. You see that a is equal to -5, and the absolute value of r is equal to 2. which again is greater than 1. So that geometric series comes in very handy. So what if we had the sum from n equals 0 to infinity of 8 times negative 3 over 4 to the power of n? Okay, so again, we know the sum from n equals 0 to infinity of a times r to the power of n is just the power of n because we're starting at 0. So we know here a is equal to 8, and the absolute value of r, which is the absolute value of negative 3 over 4, is just 3 over 4. Which happens to be less than 1. So because this is less than 1, the series converges. Okay. Now, if they come at you with the problem already in this form, those are great. Those are really easy. You're just literally lining them up and finding the absolute value of your R. Sometimes they're in this form, sometimes they're not, and you have to kind of manipulate the series a little bit to put it in this form. But once you get it in the form, you do the exact same thing. Sometimes the work is putting it in that form. All right, anyone still writing? All right. So let's say if we want to find out, let's say we want to determine if the geometric series converges or diverges. Let's say we have the sum from n equals 1 to infinity of 5 to the power of 2n times 7 to the power of 1 minus n. Okay, so we know it's a geometric series. We just have to put it in the right form to find the value of our ratio. Okay, so you want to remember that for a geometric series, the sum from n equals 1 to infinity of a times r to the power of n minus 1. And we only started at 1 because this one started at 1. If this one would have started at 0, we would have started at 0 here. So we know that when the absolute value of r is less than 1, converges. When the absolute value of r is greater than 1, diverges, or greater than or equal to 1. So that's just a little note there. Okay, so we want to rewrite this to where it's eventually going to be in this form. Okay, the first thing I would do is, of course, we're going to rewrite each factor. So let's look at 5 to the power of 2n. We can rewrite that as 5 squared to the power of n, which gives us 25 to the power of n. Which would be perfect, but we have to start at n is equal to 1, which means this is going to be n minus 1. We have to turn these to n minus 1, since we have a 1 here. If it was just to the power of n, that would be no problem because that n would equal 0. But because it's n is equal to 1, it has to be in the n minus 1 exponent. So what if we rewrite that as 25? So why did I put my 5 up there? It's 25 to the power of n plus 1 minus 1. Or we flip those around, make it minus 1 plus 1 to kind of save us a step. So we'll say minus 1 plus 1. This way we won't have to rewrite it. Okay, so that gives us 25 to the power of n minus 1 times 25 to the first power, which is just 25. Okay, so we can rewrite our 5 to the power of 2n as 25 times 25 to the power of n minus 1. So we have our n minus 1 power. And we have to do the same thing for 7 to the power of 1 minus n. So if we have 7 to the power of 1 minus n, if you remember for this one, if we have x to the power of n, that's just equal to 1 over x to the power of negative n. Okay. So we have to flip those around, which means we have to multiply those by negative 1. So that gives us 7 to the power of 1 over n is equal to 1 over 7 to the negative power of 1 over n. So if we distribute that negative, that gives us 1 over 7 to the power of negative 1 plus n, or we could just rewrite that one as 1 over 7 to the power of n minus 1. Okay, so we wrote both of those as some value to the power of n minus 1. Okay, so that means we take our original sum from n equals 1 to infinity, 5 to the power of 2n times 7 to the power of 1 minus n. At 5 to the power of 2n, we were able to rewrite that. So we have the sum from n equals 1 to infinity as 25 times 25 to the power of n minus 1. Times, we were able to take our 7 to the power of 1 minus n and rewrite that as 1 over 7 to the power of n minus 1. Okay. Now these two right here, we can just go ahead and combine those, because they're both raised to the n minus 1 power. That's the sum from n equals 1 to infinity of 25 times 25 to the power of n minus 1 over 7 to the power of n minus 1. So since they're both raised to the power of n minus 1, we can just rewrite that one last time as 25 times 25 over 7 to the power of n minus 1. Okay, so now we finally have it in the form that we need. Sum from n equals 1 to infinity of a times r to the power of n minus 1, where we can finally match these up. Okay, so we know that a is equal to 25. And the absolute value of r is just the absolute value of 25 over 7 is just 25 over 7. Uh-oh. I'm going to put that below it so I can have enough room to write next to it. Absolute value of r, the absolute value of 25 over 7, which is, uh-oh, I'm about to write the absolute value again, which is 25 over 7, which is greater than or equal to 1. So that let us know right there that the series diverges. So if they just want to know if the series converge or diverge, all you have to do is find your r and you're all set. Like I said, sometimes you might have to tweak it a little bit like this one and put it in that right form, but once it's there, it's the exact same thing. Find your absolute value of r and go from there. Now, if they ask for the sum of the geometric series, so let's say if we want to determine the sum of the geometric series, that sum from n equals 1 to infinity of 16 divided by 7 times negative 5 over 7 to the power of n minus 1. Okay, and let's say the sum of the convergent geometric series. This is what we're going to have to worry about with this one, at least not proving convergence. Which really wouldn't be that difficult because the absolute value of negative 5 over 7 is less than 1, so it would be convergent. But okay, so since the series is convergent, then we know that for the sum from n equals 1 to infinity of a times r to the power of n minus 1, that equals a over 1 minus r. And this is your sum of the geometric series, or the convergent geometric series. Okay. And again, we are going to use this formula a lot. Bless you. That means for the sum from n equals 1 to infinity of 16 over 7 times negative 5 over 7 to the power of n minus 1, we can just go ahead and match those right on up. So we know that a is equal to 16 over 7. And the absolute value of r, well, we really don't need the absolute value. We just need r now since we already know it's convergent. R is equal to negative 5, 7. Okay, so we know that that sum, from n equals 1 to infinity, I'll just write the actual sum in there, of 16 over 7 times negative 5 over 7 to the power of n minus 1, that sum is going to be a divided by 1 minus r. That 8 looks a little too much like a 9. Let me straighten that up a little. There we go. So if you plug those in, your a is 16 over 7. So it's 16 divided by 7 divided by 1 minus negative 5 over 7. Or you can simplify that to 16 over 7 divided by 1 plus 5 over 7. Or we can just make this, instead of 1, we can make that 7 over 7. So 7 over 7 plus 5 over 7 is 12 over 7. So we have 16 over 7. I'm just going to rewrite it as divided by 12 over 7. Just to kind of save some space. That gives us 16 over 7 divided by 12 over 7. So I just kind of rewrote it that way. And that division, I don't want it to look like a plus because I want to make sure that's clear. So using the rules for dividing fractions, you write down the first fraction. Your division changes to multiplication. Then we flip the second fraction. Where our 7s cancel each other out. So that leaves us with 16 divided by 12, where if we multiply each one of those by 1/4, that gives us 4 over 3. So it converges to, or the sum equals 4 over 3. All right, any questions on that one? Okay, it's still riding. Okay. Oops. So now we're going to look at section 9.3. It's your test for divergence. Okay, which states that if the limit of a series as n approaches infinity does not equal 0 or does not exist, then we know that the series from n equals 1 to infinity, make that a little bit neater, of a sub n diverges. But if that limit of a sub n as n approaches infinity does equal 0, then the test for divergence is inconclusive. And we will have to use one of the many other tests that we will learn. All right, so let's say, for example, let's say if we want to use the test for divergence, to calculate whether or not the test is inconclusive. Clean that up a little bit. There we go. So what if we have the limit as n approaches infinity of n plus 6 factorial divided by n plus 8 factorial. So if you remember with factorials, If you have n factorial, then that's just that number n times the number below it, then the next lowest number, then the next lowest number, and it keeps on going all the way till you get to 1. So 6 factorial is just 6 times 5 times 4 times 3 times 2 times 1. Okay. Now, if you had something like n plus 3 factorial, you could rewrite that as n plus 3 times n plus 3 minus 1, which is n plus 2, times n plus 2 minus 1, which is n plus 1, times n plus 1 minus 1, which is n, times n minus 1, which is n minus 1, and you can kind of see the pattern, n minus 2, and it keeps on going to you eventually get to 1. Oops. Write my 3, 2, and 1 a little bit smaller. 3, 2, 1. There we go. So again, this is just kind of a note. So if we take our limit as n approaches infinity of n plus 6 factorial divided by n plus 8 factorial, we can actually rewrite this pretty quickly. So if we take our n plus 6 factorial, we know that n plus 8 factorial is n plus 8 times n plus 7 times n plus 6 times n plus 5 times n plus 4, all the way down to eventually you get to 1. Okay, so that's n plus 8 times n plus 7 times n plus 6. If we keep on going, n plus 5, n plus 4, n plus 3, n plus 2, everything after that is just n plus 6 factorial, because it keeps going down one at a time. Okay, so we know this n plus 6 factorial and this n plus 6 factorial cancel each other out. That leaves us with the limit as n approaches infinity of n plus 6 oh, I already canceled that out. I'm already writing my final answer and didn't even get the last step in. So 1 over n plus 8 times n plus 7. Make sure I didn't skip any steps there. So again, you know the limit of a constant divided by a number that's getting bigger and bigger and bigger and bigger and bigger is always going to be 0. So we know that this test is inconclusive. All right, anyone still writing? Okay. So what if using the test for divergence, see if the series diverge or is inconclusive. And we have the sum from n equals 1 to infinity of e to the power of 3 times n divided by n. Okay, so we want to take the limit as n approaches infinity of your series a sub n. So we're going to take that limit of e to the power of 3n divided by n. Okay. So we know if we plug in bigger and bigger and bigger and bigger values, our exponent, our numerator is just going to keep getting bigger and bigger and bigger because the exponent is going to keep getting bigger and bigger and bigger. So it's just going to approach infinity. Same here in your denominator. As n gets bigger, it just gets closer and closer to infinity. Okay, well, luckily, infinity over infinity is one of our indeterminate forms. Which means we can use L'Hopital's rule. So that means the limit as n approaches infinity of e to the power of 3n divided by n is equal to the limit as n approaches infinity of the derivative of e to the power of 3n divided by the derivative of n. Well, we can rewrite that as the limit as n approaches infinity. The derivative of e to the power of 3n is just 3 times e to the power of 3n divided by the derivative of n with respect to n is just 1. Which just simplifies to the limit as n approaches infinity 3 times e to the power of 3n. But still, as n gets bigger and bigger and bigger, this whole thing just keeps getting bigger and bigger and bigger. So this limit is still just infinity. Okay, so the limit doesn't exist, so we know that this series is divergent. All right, any questions on that one? All right. So let's say, for example, again, we wanted to use the divergence test. See if the series is divergent or the test is inconclusive. So we have the sum from n equals 1 to infinity, n to the fourth power divided by e to the power of 2 times n. So again, we take the limit of our series, n to the fourth power over e to the power of 2n. And once again, if we look at the numerator, we see as n gets bigger and bigger and bigger, the numerator gets bigger and bigger. Same thing with the denominator, it just keeps getting bigger, which means we have an indeterminate form. So we use L'Hopital's rule. So that gives us the limit as n approaches infinity of the derivative of n to the fourth power divided by the derivative of e to the power 2n. Which gives us the limit as n approaches infinity of 4n to the third power for our numerator divided by 2 times e to the power of 2n for our denominator. Okay. What we see here is n gets bigger and bigger and bigger and bigger and bigger. Our numerator is still infinity. Same with the denominator. It just keeps getting bigger and bigger and bigger. So we're just going to use, since it's an indeterminate form again, we're just going to use L'Hopital's rule again. I don't know why I started to put parentheses around that. Don't need parentheses around that. So now we have the limit as n approaches infinity, but we use it on the previous series. So I swear it has to be some way to turn up that series thing. So we have the derivative of 4n to the third power divided by the derivative of 2 times e to the power of 2n. Okay, so that gives us the limit as n approaches infinity. So if we take that derivative, that gives us 12n squared divided by, we take the derivative of e to the power of 2n, that's 2 times e to the power of 2n, multiplied by the 2 that's already there, it gives us 4 times e to the power of 2n. And we can see that if we keep plugging in numbers that are bigger and bigger and bigger, numerator approaches infinity. Same thing with our denominator, just gets closer and closer to infinity. So it's an indeterminate form again. So we have to use L'Hopital's rule again. Keep using it until we eventually do not end up with an indeterminate form. So now we use L'Hopital's rule on this version of it. So we have the limit as n approaches infinity of the derivative of 12n squared divided by the derivative of 4e to the power of 2n. Okay, so that's going to equal the limit as n approaches infinity. The derivative of 12n squared, bring down the 2, multiply it by the 12 that's already there. It gives us 24n divided by the derivative of e to the power of 2n is 2 times e to the power of 2n. Multiply it by the 4 that's already there. We have 8 times e to the power of 2n. Okay. So again, if we see that n is approaching infinity, and our numerator is just going to keep getting bigger and bigger and bigger. Same with our denominator. It's going to keep getting bigger and bigger and bigger. So it's an indeterminate form once again. So we have to use L'Hopital's rule again. So now we apply L'Hopital's rule to this version of it. So we have the limit as n approaches infinity of the derivative of 24n divided by the derivative of 8 times e to the power of 2n. So that's going to equal the limit as n approaches infinity of the derivative of 24 times n. Well, the derivative of n is just 1. So 24 times 1 is 24. Divided by the derivative of 8 times e to the power of 2n. Again, the derivative of e to the power of 2n is 2 times e to the power of 2n, multiplied by the 8 that's already there, and that's 16 times e to the power of 2n. Okay, so good news is we don't have to apply L'Hopital's rule anymore. But if you go ahead and have a value where you have a constant as a numerator divided by a number that's getting bigger and bigger and bigger and bigger and bigger, that limit is just going to equal 0. So after all of that, we know that the test is inconclusive. And don't worry, we'll learn quite a few tests to use when this one's inconclusive. All right, any questions on that one? Okay, anyone still writing? Okay, so now we are going to look at the integral test. Excuse me. Okay, so let's say if we know that f is positive, continuous, and decreasing. For x is greater than or equal to 1, don't really need that comma just yet. And for a sub n equals f of n. For the a sub n equals f of n, that's decreasing for n is greater than or equal to some larger value that we will call uppercase n. Now, all of these stipulations are met, then we know that the sum from n equals 1 to infinity of a sub n, excuse me, and the integral from n to infinity of f of x with respect to x, either both converge or both diverge. Excuse me. Okay, so let's say, for example, if we just want to determine if the integral test can be used for the series, so let's say you have the sum from n equals 1 to infinity of 2 divided by the cube root of 4n plus 5. Okay, so you can replace this with x if you want to. You don't have to. I just keep it as n. So we're going to look for it to be positive, continuous, and decreasing for n is greater than or equal to 1. Okay, so we plug in n equals 1, we get a positive number. N equals 2, get a positive number. Any number greater than 1, we'll get a positive number for this whole thing. Okay, so we can see that it's positive for n is greater than or equal to 1. So that one checks. Okay, now we want to see if it's continuous for n is greater than or equal to 1. Okay, well, one thing we know about this one, because it's in the denominator, we know that 4n plus 5 cannot equal 0. which means if we subtract 5 from both sides and divide by 4, we know that n cannot equal negative 5 over 4. Okay, which means it's continuous everywhere else. Well, since we're only worried about n being greater than or equal to 1, that negative 5 over 4 means absolutely nothing to us. So it's continuous for every value except n equals negative 5 over 4. So that's not even in our domain of n being greater than or equal to 1. So we know it's continuous there, so that one checks. Okay, so if we plug in values for n that's getting bigger and bigger and bigger and bigger and bigger, then its whole series is just going to keep getting smaller and smaller because you have a constant divided by a number that's getting bigger and bigger and bigger and bigger. So we can see that this as a whole is just going to keep decreasing. So it's decreasing for n greater than or equal to 1. So it actually covers that one. Okay. So our a sub n is a function of n, which covers that one. So we can see that since it covers all the bases, all the stipulations, we know that we can use it. So the integral test can be used for the sum from n equals 1 to infinity. That was a messy looking infinity. There we go. Of 2 over the cube root of 4n plus 5. Okay. Now, they didn't want us to solve it. They just wanted us to find out if we could use the test. All right. Let's say, for example, we wanted to apply the integral test to the series, to the sum from n equals 1 to infinity, and divided by n squared plus 1. Okay, so we can see that for n being greater than or equal to 1, this whole thing is positive. So you plug in 1, it's positive, 2, it's positive, it'll keep on going. It's always going to be positive. So it's positive. Okay. And there are no undefined values for n being greater than or equal to 1. Plug in any number equaling 1 or larger, you will have a defined value. So it's continuous. Okay, so we notice the denominator is actually bigger than the numerator. So as you plug in larger values, the denominator grows faster, which means this is just going to keep getting smaller and smaller. Okay, so and it's decreasing. For n is greater than or equal to 1. Okay, so we can actually apply the integral test. So just if you want, you can use it with respect to n, but I always change to f of x. Just replacing the n with x. So that's x over x squared plus 1. So that means we're looking for the integral for n is greater than 1. So we know from 1 to infinity of x over x squared plus 1 with respect to x. And again, if you left it at n, it would just be with respect to n. Only difference. Okay, so with this one, we can actually solve this one using u substitution. So if we have the integral of x, and I'll just move the dx up top, divided by x squared plus 1, we're going to let u equal x squared plus 1. Oops, straighten it up. Which means our du, derivative of u, is just going to equal 2x plus the derivative of 1, which is 0, so 2x with respect to x. So if we divide both sides by 2, we have du divided by 2 is equal to x dx. Or we can say 1/2 times du. Either one works. Okay, so that means we end up with the integral of 1 to infinity, and actually move this equal sign over a little bit. Give us a little bit of room in front of the integral. That x dx just turns into du over 2. And that 1/2, we can just factor that right out to the front. Divided by x squared plus 1, oh, that's our u. So we have the integral of du over u, which gives us 1/2, and the integral of du over u is just the natural log of u. From 1 to infinity. Okay, but we know going from 1 to infinity. Oh, I didn't know what that was. So we know going from 1 to infinity, we can't just plug in infinity. That's just 1/2 times the limit. And you can use t or b or whatever you like. It says b approaches infinity of the natural log, and we'll go ahead and replace that u with x squared plus 1. And that's from 1 to your value b. Okay. Because x squared plus 1 is positive for all real numbers, you don't really need the absolute value, but I'll put it there anyway. Okay, so that gives us 1/2 times the limit as b approaches infinity. Plug in, we get the natural log of b squared plus 1 minus the natural log of 1 squared plus 1. Okay, so if we take the limit of the first term, the natural log of a number that's getting bigger and bigger and bigger and bigger and bigger is just a number that's getting bigger and bigger and bigger. So if the argument is getting bigger towards infinity, then the whole value is increasing towards infinity. So honestly, this is just infinity. And you could say this is minus natural log of 2, not that it makes a difference, because this infinity means that the whole thing is to infinity. Okay, so we can see that the integral diverges. So if the integral diverges, then we know that the series also diverges. So since the integral diverges, we know the series diverges. All right, any questions on that one? Okay, so the next test we're going to look at will be the p-series and harmonic series. Which we will have tests for those also. Okay, so let's say we have a series, and that series is in a very specific form of the sum from n equals 1 to infinity of 1 over n to the power of, let's say, p. Where if we plug in n equals 1, that's 1 over 1 to the power of p plus 1 over 2 to the power of p plus 1 over 3 to the power of p. And it keeps on going till you reach some finite value n to the power of p. And because it goes to infinity, you're going to go past that too. Make that p a little clearer. Okay, so if it's in its form, this is a p-series. We know that p is a constant. Okay, now a very specific type of p-series happens when p is equal to 1. So when p is equal to 1, that means we have the sum from n equals 1 to infinity of 1 over n to the first power. Then that's just 1 plus 1/2 plus 1/3 plus 1/4, and it keeps on going to just some finite value 1 over n and passes that up to. Okay, so this specific version of a p series when p is equal to 1 is called a harmonic series. A harmonic series. And you're going to see a whole lot of formulas where just making one little change will give it a completely different name. Now, sometimes you can get that harmonic series and you can write it, instead of being 1 over n, you can write it as a linear function in your denominator. And that would just be a general harmonic series. Okay, so again, this is just a little side note. A general harmonic series can be written in the form. So we have the sum from n equals 1 to infinity of 1 over a times n plus b, where a and b are constants. Okay, so even though n is a linear form already, you can write it in a different linear form. All right. So let's look at our p-series test, where we have the convergence of the p-series. Okay, now the p-series, remember that's the sum from n equals 1 to infinity of 1 over n to the power of p, which is just 1 over 1 to the power of p plus 1 over 2 to the power of p, 1 over 3 to the power of p, and keeps on going. Clean up that a little bit. Okay, so we know that if p is greater than 1, it converges. And it diverges when p is less than or equal to 1. Bless you. So let's say, for example, we wanted to determine the convergence or divergence of the p-series, say the sum from n equals 1 to infinity of 1 over the fifth root of n, and that'll be problem A. And for problem B, we have 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25 plus, and it keeps on going. Instead of 5 to the power of n, let's make this fifth root of n. So make that the fifth root of n. Okay, so if we look at problem A, the sum from n equals 1 to infinity of 1 over the fifth root of n, we can rewrite that as 1 over n to the 1/5 power. So we see that p is equal to 1/5, which is less than or equal to 1. So we know it diverges. And that's it. Okay, now for problem B, we have 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25, and it keeps on going. Well, we can rewrite each one of those terms. So 1, we can rewrite that as 1 over 1 squared. At 1/4, we can rewrite that as 1 over 2 squared. At 1/9, we can write that as 1 over 3 squared. At 1/16, we can rewrite that as 1 over 4 squared. At 1/25, we can make that 1 over 5 squared. You probably see the pattern right now, which means we can rewrite that whole thing as the sum from n equals 1 to infinity of 1 over n squared. We can see that right here, your p is equal to 2, which is greater than 1. So we know it converges. All right. So let's say, for example, if we wanted to determine the convergence or divergence for the series, let's say for A, we have the sum from n equals 1 to infinity of 1 over n to the 7/8 power. And for B, we have the sum from n equals 1 to infinity of n to the power of 5 times e divided by n to the power of 7 pi. Okay, now the ones in the form of A, they're pretty quick to deal with. Because all you have to do is see that P is equal to 7/8, just less than or equal to 1, so we know it diverges. Okay. Now with B, as long as your bases are the same, you can still put it in the P series form. Okay. You just have to remember you have x to the power of m divided by x to the power of n. That's equal to x to the power of m minus n. So that means if we have the sum from n equals 1 to infinity of n to the power of 5e divided by n to the power of 7 pi, that's just equal to the sum from n equals 1 to infinity of n to the power of 5e minus 7 pi. Okay. But we don't need it as n to the power of something. We need it as 1 divided by n to the power of something. So we still have to tweak it a little bit more. So also we have to remember that if we have x to the power of m, we can rewrite that as 1 over x to the power of negative m. Okay. Just move it to the denominator, make the exponent negative. So that means we can rewrite this as the sum from n equals 1 to infinity of 1 over n to the power of negative 5e minus 7 pi. Okay. Or if we go ahead and distribute that negative 1, that gives us the sum from n equals 1 to infinity of 1 over n to the power of 7 pi minus 5e. Okay, so we can see right here that our p is equal to 7 pi minus 5e. Well, if you plug that into your calculator, you would get approximately 8.4, which is still greater than 1. So since our p is greater than 1, we know it converges. All right, anyone still right? Oh, still right there. Okay, so let's say, for example, if we wanted to determine whether the series converges or diverge. And we have 1/3 plus 2 divided by 3 times 2 to the third power plus 3 divided by 3 times 3 to the third power plus 4 divided by 3 times 4 to the third power plus 5 divided by 3 times 5 to the third power, and it keeps on going in that pattern. So with this one, you can just rewrite it. Instead of 1/3, we can make that 1/3 times 1 to the third power plus 2 divided by 3 times 2 to the third power plus 3 divided by 3 times 3 to the third power plus 4 divided by 3 times 4 to the third power plus 5 divided by 3 times 5 to the third power. And that actually gives us the sum. I'll put that underneath it, make sure I have enough room. From n equals 1 to infinity, we see here, each one of those moves up 1. It starts at 1. So n divided by, we see the 3 is a constant, so that stays right with it. And the 1 to the third, 2 to the third, that value changes and increases 1 at a time, so that's n to the third power. Okay. But if we simplify this n cancels out with one of these n's, so this just ends up being n squared. So that's the sum from n equals 1 to infinity of 1 divided by 3 times n squared. Okay, so if we get that 1/3 and factor it out to the front, that's 1/3 times the sum from n equals 1 to infinity of 1 over n squared. So we finally have the form we're looking for. We know that p is equal to 2, which is greater than 1. So we know it converges. All right, any questions on that one? All right, straighten those up. Okay, so I will stop there. I won't go over the limit comparison test until Monday. Plus, you have the test, so I don't want to throw too much at you at once. So if you have any questions, of course, feel free to ask. If not, I will see you on Monday. Freeze that screen. Put that there. There we go. All right, you too. You too. Oh, let me start 194.
Have a nice day.
You too. All right. You too. All right. Let me go ahead and grab the sum of a convergent geometric series. All right. Let me move this out the way. Okay. Oops. Here we go. Was it this page or was it one? Oh, sorry about that. I forgot I froze the screen. Was it this one or one of the following pages? Okay, let me know when I get there. All right. All right. Okay. Okay. Let me know if I have to go up or down. Oh, actually, I can probably just zoom out a little bit. You can probably get the whole thing at once. I don't want to make it too small. Oops, sorry, there we go. And let me know if you want me to move it up. All right, perfect. All right, Donovan, you have a good day too. Do, do, do. Let me go ahead and start this video processing.